Okay, I wanted to take this time to go over a couple of examples for you and some of the questions that popped up in Module 7, which turned out to be kind of more difficult, at least to get started. But once you get started with some of these problems, it becomes pretty self-explanatory and it becomes a lot easier. But it definitely does take practice. I want to start off with this one, which always seems to come up with questions when students approach this. So the question is, what is the probability that 7 letters you typed, or assuming we have a typing board with all the letters of the alphabet, but no letters are repeated? So writing this out in probability notation, I don't want to use yellow, so I'm going to change this over here. Make it a little thinner. We're looking to find the probability that we have no repeats, basically, with 7 letters being typed. So probability of no repeats. Let's get a little bit messy there. But the general idea is 7 letters are being typed. So that tells us we have 7 events occurring. Each time we type a letter, there's going to be a probability. So you kind of picture this, 7 different lines, each representing an event. And we know that when we have separate events, one following each other, the operation we're going to use is the multiplication rule for each one. So starting out with the idea that we have no repeats, our sample space, of course, is the 26 letters that are on the keyboard. And so the question becomes, for the first letter, what is the probability, or what number of letters, if we're looking at our event space, which ones would be successful, how many of these 26 would be considered successful, meaning we wouldn't be repeating something that's already been typed? And so with the first letter, we actually have 26 letters to select from, all of which would be non-repeats of previous letters, because we haven't typed any letters yet. And then for the second letter, we still have all 26 keyboard letters to choose from, but now only 25 are considered ones that we would not be repeating, and that's because we've already selected a letter here. So there's one less letter to choose from. And then just goes down the row. It'd be 24 now, 26, and so on and so forth, until we get down to 7 letters. Finding the product of all these gives you the probability of that event. The tricky part here is that first one. Realizing that on the first one, we have a 100% chance of not repeating everything. There's 26 out of the 26 letters that we can successfully pick that would give us a no repeat. Okay, so let's move on to the next one. A little bit more difficult, but similar idea. In this case, we're picking 5 people from the population. Again, each one of those is an event. The question is, what is the probability, and here's the tricky part, that at least one of them has been vaccinated? Now, one of the ways that we can picture this is with a tree diagram. I'm going to go ahead and move this down a little bit so we can get a little more space. Because a tree diagram only gives us a view of what's possible here. Now, with 5 people, my diagram can get really messy really quick. It'd be really long. There'd be 32 possible paths. So I'm going to change this to 3, just for ease of explanation at this point. This will still give me 8 different outcomes. So the first pick would represent the first string on my tree, where they would either be vaccinated or not vaccinated. This represents my first person that I select. And then we do a second one. Again, each one of these has a branch that comes off of it. It's either going to be vaccinated or not vaccinated, vaccinated or not vaccinated. Then we do a third branch, vaccinated, not vaccinated, vaccinated, not vaccinated, vaccinated, not vaccinated. Now, you don't have to draw this. I'm drawing this so I can illustrate a couple of concepts: vaccinated, not vaccinated. Okay, the question asks us, at least one. One of the things that we've talked about in previous videos is how whenever we see at least one, that there's a complement to that. So let's just say at least one, x is greater than or equal to 1. The complement of greater than or equal to 1, which is at least 1, is 1 minus the probability of none. Always. So looking over at my diagram, there's only one way that none of the people can be vaccinated. In other words, this path right here. None, none, none. And I thought this would highlight it, but it's actually drawing over it. So I'm going to go back to my little stroke here called black. And re-put this in. There's an N here and an N here. Alright. The whole point was to highlight that. But you can see that along this tree, there's only one path where none of them have been vaccinated. And if you look at every other branch, they have at least one person who has been vaccinated. For example, if we go along here, we could go none and then vaccinated and then not vaccinated, or not vaccinated and vaccinated. And if you look at any one of these other paths, all of these have at least one. For me to be able to calculate this probability, I would have to find the probability of each of these paths, and then I would add them all up. That would be a very daunting task, especially if you're dealing with 5 people instead of just 3. As you can see, there's 7 paths where we have at least one. So for this, you would have to find the probability of vaccinated, vaccinated, vaccinated. That's this row here. Then you would have to add to that vaccinated, vaccinated, not vaccinated. And you have to add to that the next path, vaccinated, not vaccinated, vaccinated, which is going, vaccinated, not, and vaccinated. And you'd have to keep on going until you got to the last one, which was not vaccinated and not. Or I'm sorry, not vaccinated would be the other one. The last one, not, and then vaccinated would be the last one. The better way to do this, and this is true whenever you see these keywords here, at least one, is to use the complement. The sum of these 7 paths is going to be equal to 1 minus the probability of this last path, which is not. So 1 minus not, and really we want to find the probability of not, P around that. Well, the probability of not, if 51% of them have been vaccinated, then we know 49% of them have not been vaccinated. So 0.49 times itself 3 times is the same as 0.49 raised to the 3rd power. And if we calculate that, we find the probability of x being at least 1. Go ahead and calculate that on your calculators. I don't have it right next to me. Let me pause this for a second. You should get as a result 0.8824. So there's about an 88% probability that at least one person is vaccinated when you take a sample of 3 people. Alright, so let's move on to the next one, which I have down here at the bottom. I think I'm actually going to have to get a new page, so I'm going to pause the video. Here's another problem that I get a lot of questions on, and this again has the same principles as the last one, but you really have to work out, maybe draw some pictures as to what they're talking about here to kind of get an understanding of it. So the question goes, when doing blood testing for viral infection, the procedure can be made more efficient and less expensive by combining partial samples of different blood specimens. If samples from 4 people are combined and a mixture tests negative, we know that all 4 samples are negative. The question is, find the probability of a positive result for 4 samples combined into one mixture, assuming the probability of an individual blood sample testing positive for the virus is 0.5. So I'm going to draw a little picture here to kind of illustrate this. The way this works is we have 4 different blood samples, 4 different circles, and from these 4 circles, we take little samples, and all these little samples of the blood are put into one mixture. That is our blood sample mixture. They also do this with CDs on another problem. But basically the idea is if any one of these 4 tests positive, it's going to affect this mixture sample that I have. However, if every one of these is negative, then my overall mixture is going to test negative. So the only way I can get a positive result is if at least one, at least one is positive. So the only way we get positive is if at least one tests positive. In other words, maybe this one is positive. If that's the case, it's going to infect this. Or maybe one of the others is positive. Or maybe 2 of them are positive. Or maybe 3 of them. Or all 4 of them are positive. In any of those cases, at least one is positive equals positive result from my sample. So the only way we can get at least one positive is if one or more of them are positive. And so we'd have to find every path and in every order in order to find the probability, just like on the previous example. The better way to do this is to use the complement rule. 1 minus the probability that they're all negative. So again, negative, 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 negative for all 4 samples. Since the probability for testing positive is 5% for each individual, if we go 1 minus, the probability that they'll test negative is 95. So you have 0.95 times itself 4 times, or 1 minus 0.95 to the 4th power. This will calculate the probability that at least one will be positive. I hope this helps you work through some of these problems. Look for that whole at least one. Sometimes they'll say it's outright, sometimes they won't. But in every case, at least one, you always want to find 1 minus the probability of none.